All right, in this video, we're going to finish out chapter 12 for Chem 102. We're going to talk about phase changes. So a phase is just a homogeneous part of a system that's separated from the rest of the system by a well-defined boundary, like a melting point, a boiling point, a boundary of like okay, we've crossed over from solid into liquid, right? Like clearly all of our intermolecular forces are now different. Our distances are now past a certain point. So there's phase changes that you already know, hopefully. Freezing, right, is liquid to solid. Evaporation or vaporization is liquid to gas. Melting, we also call fusion, is solid to liquid. Condensation, gas to liquid. Sublimation, solid to gas. So 6 possible phase changes. We talked about all of them except deposition is gas to solid, opposite of sublimation. So here's a list here of just things to make sure you remember the names of those phase changes. And what we're doing when we're going from phase to phase up here, so these are all endothermic, right? Separating particles requires breaking of intermolecular forces. So kind of like breaking bonds, putting in energy to break apart and add space. Now, if we want to go down, that's exothermic because we need to remove energy to slow the particles down so that they can have more attractions to each other to get into those more closer packed particles. The boiling point is vapor pressure equals external atmospheric pressure. That's the temperature that we're looking at when we actually get to fully become gas. We call the molar heat of vaporization or delta H vaporization. We've talked about that already, is the amount of heat that you need to vaporize 1 mole of substance at its boiling point. So if you're already at the boiling point, you got the right temperature, how much heat you have to put in to do that. So it's not just get to that temperature and now you're all your liquid's gas. You actually have to put in energy once you get to that temperature, right? You know that as soon as you reach 100 degrees, it doesn't poof, all of your liquid is now gas. You have to put in energy at that temperature now. Once we reach that point where we're allowed to boil, now we got to put in energy to do that. So that's that heat of vaporization. So you can look here at the heat of vaporizations and the boiling points, and you can think about what are different between these things, why they have different boiling points, and I bet you can consider maybe why some of these things have different heats of vaporization as well as boiling points. The critical temperature of a substance is the temperature above which gas cannot be liquefied anymore. So if you get to the point where you can't turn your gas back into a liquid, and the critical pressure is the pressure that you need to get to that critical temperature. So we call that the critical point, is a critical temperature and critical pressure. And again, we can kind of think about intermolecular forces, but this should be pressure ATM and temperature in Celsius, sorry. Solid liquid is fusion, and that's melting. And then freezing would be liquid to solid. Melting point or freezing point is the same number, it's the same temperature. Why it doesn't bring over? This is at equilibrium, just like what we talked about with the vapor pressure kind of going back and forth. This one also is at equilibrium. So ice and water are at equilibrium with each other. They go back and forth, just like the vapor pressure, the liquid goes back and forth to the gas phase. And so they're occurring at the same rate once we reach equilibrium. So you can get to a point where you can't tell that there's something changing. So with phase changes, we can talk about a few different graphs. The first graph is a heating curve. So take a look at this heating curve. As we increase temperature over time, and I will also say that this bottom could be heat. So I don't want to say just, we're adding heat as we go. So I want you to know that we're increasing heat as we go. The heat is being continually added over the time. So we start out with solid, which makes sense. We add some heat, our temperature goes up, which makes sense. We get to a certain point though, and we keep adding heat, but the temperature doesn't go up. That's interesting. All right, when we get to this next point, we start adding heat again and temperature goes up, which makes sense. Then I get to this point and I start adding heat, and again, the temperature doesn't change for a while. And then we get to a point where eventually the temperature does start rising again. These flat lines, something is happening in these flat lines. This is your melting and your boiling point. This is where we are doing that phase change. So like I said before, it's not just liquid, poof, we're gas. We have to put in energy to take all the liquid and turn it into gas. So these are no change in temperature happening here, but we're still adding energy. So if we're thinking about math stuff, which maybe you are, if you have a sloped line, we can use Q equals mc delta T because we have a change in temperature. So on your sloped lines, you can use Q equals mcat. But on our flat lines, we can't use that. So we have to use the enthalpy of that phase change. And so your Q would be equal to your change in enthalpy here. But just make sure you're looking at your unit. So for example, if this is kilojoules per mole, then your Q is only in kilojoules. You'd have to divide it by moles to get that. So we could take, let's see, I could do Q over N, and then we could do Q is equal to the moles N times the delta H. And that's going to be for both of those flat lines. The first delta H here would be delta H of vaporization. This one would be delta H of fusion. So you can imagine now how I can develop a problem where I say, here, go from this point to this point, and you have to use both this Q equation and this Q equation. But no, you cannot use the delta T one unless if your temperature is flat. So the heat of fusion is the energy needed to melt a mole of solid. We can look at the melting points and the heats of fusion for these substances as well. And then you have, of course, sublimation, deposition, and we talked about the enthalpy of sublimation, would just be the same thing, 1 mole of a solid turning into its gas. So sublimation would be the same as the fusion plus the vaporization all in one step. So we could actually figure out the enthalpy of sublimation kind of by using Hess's law and applying both of those. So why don't you try this example? Go through it and think about what formulas you need to use for each part. You can use this table or this graph here to help you visualize what's going on and the formulas you'll need to use. So try that out. I'll take you back to the question. If my iPad will work. And then come back when you get stuck or if you think you have an answer. Okay, so there's a whole bunch of strategy here, but basically I want to show you, we can find each part. So the first part, you will have a change in temperature, and you would use mc delta T to find your Q for the first part. It's negative for this because we're decreasing in our temperature, going from 100 down to 37. Then we stop changing temperature, and we have to do the phase change. So now we do the phase change, we take our mass, turn it into moles. Moles gets plugged in for N, use our vaporization, and then it's going to be opposite because it's exothermic when we're going from gas to liquid, right? Condensation. So we just change the signs as we need it. And so we have two kind of things happening right now. We have the change into temperature, which is this one, and then we have the phase change. And so putting that together as right now, totaled of that much energy. And then if we want to keep going, we now have another temperature change. So we'll use Q equals mcat. We're just tallying these up. So we're warming the water, so they'll be positive. And then we want to use heat of fusion because we're going from solid to liquid. And then we're going to add them up. So don't think too much about it. Break it into little tiny pieces, and that can be helpful. Again, we'll do some practice in class. A phase diagram is basically showing you at what temperature and pressure conditions do you have solid, liquid, or gas. I want you to remember for phase diagrams, this looks like a cup, kind of. I know it's not really, but it looks kind of like a cup, a chalice, like a wine glass or something, right? The liquid goes in the cup, and then decrease your temperature from liquid, you get solid. Increase your temperature from liquid, you get gas. Or they're calling it vapor here, but it's also gas phase. So that's how you can orient yourself. Find the liquid in the cup, in the glass, and then it would be solid and then gas on either side. This point here, where you can have all three solid, liquid, and gases, is called the triple point, because we can have three different phases. Notice that your pressure of this substance in normal atmospheric pressure has a melting point. So this crossing this line is your melting, sublimation point, solid to vapor. Crossing this line is your melting point. Crossing this line is your vaporization point. So if you cross over, you're changing phases. So you have to read a graph like this. I maybe would tell you like, hey, if you had this point and I gave you some numbers on the side, what would the pressure be? And if I decrease the temperature, what would happen? So if we decrease the pressure, it would go down into gas. If we had a gas at this point and we increase the pressure, it would go up into a liquid. So just think about where you are on the graph and then what the question's asking you for, and these don't have to be too complicated. Notice that this phase diagram, the big thing I want you to notice about this first one is that it has an increasing slope here, which means that if we have a liquid and we apply pressure to it, it'll turn into a solid, which makes sense because we know solids are more, in general, more compact than liquids. However, let's look at water. Water is the opposite. If we have a liquid here and we increase pressure, it's going to stay liquid. But if we have a solid at this point here and we increase pressure, it would turn into a liquid. This is how we're able to ice skate, right? We put pressure on ice and it turns into a liquid, so we're able to glide. If this one were more like carbon dioxide, for example, you couldn't ice skate on carbon dioxide. I remember that being in a practice MCAT question when I was doing MCAT test prep. Is to kind of explain the process of why we could use water but not carbon dioxide to ice skate on. It's because if you take carbon dioxide solid and you put pressure on it, it's going to stay solid, so you'd be skating on more solid. You wouldn't get that liquid feel. But water, if you put pressure on at 1 atmosphere, it's really easy to go into the liquid phase. So why don't you try this question? Determine the normal boiling point and normal melting point. Determine the physical state of the substance at 2 atm and 110 degrees C, and determine the pressure and temperature corresponding to the triple point. So I'll zoom in so you can screenshot that if you want to. I'll zoom in on this so you can see those numbers a little bit better. Okay. So we're just going to label stuff. So first point, the normal boiling point. So normal boiling point is the point at which we go from liquid to gas at 1 atmosphere. So I find 1 atmosphere, and I go from liquid to gas right here at 200 degrees. So that's my boiling point. This would be my melting point, right? From solid into liquid, because liquid goes in the cup, so I have solid, liquid, and gas. So this is my boiling point, and then here before 150, maybe like 140 would be my melting point. So they guess like 205 and 140 for your answers for that. At 2 atm and 110, so 2 atm, 110, we're just plotting right here. Where are we? We're solid because it's solid, liquid, gas. Remember, liquid goes in the cup. And then where's the triple point? The triple point is the point in which you have that kind of bottom of that wine glass, the bottom of that cup where it goes into the stem. We have a triple point at maybe like 0.8 atm and like 105, 110. They said 115 here. Again, on a test or something, if we asked you a question like this, we would have a range of values that made sense. Just don't tell me that the pressure, this pressure here would be 1.5 or something. Like it has to be reasonably in between those two values that you're given points for. So not too bad as far as the phase diagrams. I think the most difficult part about everything in this video would just be calculating all those heat changes. So Q equals MCAT and then Q equals N times your delta H. Just know you cannot use Q equals MCAT if you don't have a temperature change. And we don't have a temperature change when we're doing those phase changes. So make sure to use those enthalpies instead. And here's a little summary over the things we talked about. I don't think it's actually finished. The PowerPoint messed up for me, but this is all for chapter 12, and we'll see you in class.